So let's dive into a really cool story about two different ways to teach an AI how to deal with the real world. It's a tale of two learning styles, a head-to-head competition, and it gets at a really fundamental question about how anything learns, really. I want you to imagine you're trying to teach a robot a really complex skill, like, say, balancing a bunch of poles on top of each other. Now, you could just let it try and fail over and over and over again for millions of attempts. Or what if you could give it a little hint, a cheat sheet with the basic laws of physics already filled in? And this gets right to the heart of a massive challenge in robotics. The big problem is that learning from scratch takes an unbelievable amount of time and data. We are talking millions of real-world trials, which is just crazy impractical and expensive when you're working with actual hardware. This whole problem actually has a name. It's called sample efficiency. And it's basically just a measure of how fast an AI can learn something. Think of it like learning to ride a bike, right? High sample efficiency means you figure it out in maybe 10 tries. Low efficiency means you need like 10,000 tries. Obviously, we want our AIs to be as efficient as possible. So, to try and tackle this efficiency problem, some researchers set up this brilliant competition. They decided to pit two kinds of AI against each other, and each one had a totally different philosophy on how to learn about the physical world. So, in one corner, you've got the black box learner. This is your standard AI that has to figure out all the rules of physics just by watching things happen. And in the other corner, you have the physics-informed learner. This one gets a major head start because the fundamental laws of motion are already baked right into its design. Okay, let's talk about the black box AI first. It's a powerful tool, no doubt, but it starts out completely naive. I mean, it has zero built-in understanding of concepts we take for granted, like energy or momentum or even gravity. It has to discover every single rule of the universe all on its own, just through trial and error. But then you have the physics-informed AI. This is the one with the cheat sheet. Its whole architecture is built around a concept from classical mechanics called the Lagrangian, which is really just a fancy way of describing a system's energy. So, because its very structure is based on this physical truth, it has a powerful built-in assumption. It knows that energy must be conserved. It doesn't have to learn that rule, it knows it right from the get-go. So you've got your two contenders. How do you test them? Well, you create two very, very different arenas. One is pretty simple and predictable. The other? It's complex, it's volatile, it's chaotic. First up, the stable arena. Think of this as the easy mode. The tasks are things like balancing a single pendulum or just one pole on a cart. In these kinds of systems, small mistakes aren't catastrophic. The system is pretty forgiving. It doesn't just spiral out of control if you're a little bit off. And then they cranked the difficulty way, way up. The chaotic arena features these incredibly hard tasks, like balancing 3 poles on a cart at once. These systems are the total opposite of stable. They are unbelievably sensitive, and the tiniest little error in judgment can lead to immediate catastrophic failure. This is that famous idea, right? The butterfly effect. A tiny change at the beginning, a minuscule error in predicting what's going to happen next, can grow exponentially, leading to a completely different and usually disastrous outcome. This sensitivity, this is the ultimate test of how well an AI really understands physics. Okay, so the stage is set, the contenders are ready, the challenges are brutal. So, who won? Let's take a look at the data. So, if we look at the results for the simple pendulum task, you can see both AIs pretty much nailed it. The blue line here, that's our black box AI, and the green line, the physics-informed one, both of them get a high score. In a simple world, it's basically a draw. But now, look what happens when we get to the chaotic task. The story just completely flips. Follow that green line, that's our physics-informed AI. It soars up and masters the challenge beautifully. Now look at the blue line, the black box AI. It just flatlines. It completely fails to learn anything at all. The difference is absolutely stunning. So the big question is, why? Why was having that physics cheat sheet such an unbelievable superpower when things got really complicated? The answer is so cool, and it all comes down to how these AIs practice. See, to get around that whole sample efficiency problem, both AIs learn by running millions of practice scenarios inside their own digital minds. The researchers call them imaginary trajectories. It's kind of like a boxer visualizing a fight before it ever happens. And as any athlete will tell you, the quality of that visualization is everything. This slide shows us, visually, the quality of that imagination. These graphs are plotting the prediction error over time. Just look at that blue line for the black box AI. It skyrockets. Its imagined world almost immediately drifts away from what's actually real. But the green line, for our physics-informed AI, stays incredibly low and accurate. Its imagination is grounded in truth. And that is why this matters so much in a chaotic system. Any tiny little error the black box AI makes in its internal simulation gets magnified in the next step and then magnified again and again until its entire practice session is based on totally nonsensical, impossible physics. Its imagination becomes worthless for actual learning. And this graph, this is the smoking gun. This shows us the root cause of the whole problem. It's plotting the energy error in the AI's imagination. That blue line just shoots up, which means the black box AI is constantly imagining futures that violate one of the most basic laws of the universe, the conservation of energy. It's basically imagining magic. The physics-informed AI, though, it can't do that. Its very structure is built on the principles of energy, so its imagination is literally constrained by reality. It is incapable of imagining a physically impossible future. And that means every single one of its practice runs is realistic, grounded, and incredibly effective for learning. So let's zoom out. What does all of this mean for the future of AI and for building smart machines that can actually operate in our world? Well, the key takeaway here is pretty profound. For simple problems, yeah, a blank slate AI can figure it out. But for the complex, chaotic problems that really define our world, giving the AI a head start with built-in knowledge is a total game changer. These built-in rules, what researchers call inductive biases, act as a powerful guide when the going gets tough. You know, this whole experiment suggests that instead of just hoping an AI will magically rediscover Newton's laws from scratch, a much smarter path might be to just build in the foundational principles that we as humans already spent centuries figuring out. This could be the real key to unlocking that next generation of efficient and reliable robots. And that leaves us with this really fascinating final question for how we go about building the intelligence of the future. Is the goal to create a learner that starts from absolutely nothing, or is it to build a partner that can stand on the shoulders of giants, using all the collective wisdom of human science as its foundation?